Well, hello. I'm creating a little video for you to just get introduced to the concept of Gauss's law. I describe Gauss's law in my class as maybe one of the weirdest concepts, the one that doesn't seem to flow with everything else that we do in physics, and particularly electricity and magnetism. And it is unique in a way in that it's very simple, but it's a very powerful and useful tool if you understand it very well. So this is just going to be an introduction. I'm not going to show you nearly everything that it can do, but show you some very simple and almost silly things it can do, and also some very practical and important questions that it can answer as well. So in the box on the screen is a statement of Gauss's law, and it includes some things that I hope by now you've recognized. By now you should have seen the concept of electric flux, and so we have here the symbol for electric flux, which is the Greek letter phi, usually capital Phi. We'll put a little e because this is an electric flux. We will see later in the course of magnetic flux. And then the way we've calculated flux in most situations is through simple multiplication of electric field strength times the area through which that field is piercing. But usually you're going to see this written as the sum of a bunch of things that are multiplied. And this is just more useful if you have a field that is not uniform over a particular area and you have to rely on integration. I will tell you that's a very, very unusual thing. Usually we'll set it up this way to make it look like a calculus problem, but then we'll simplify things and say, oh, we really don't need calculus at all. So that's that middle statement there, just really the definition of electric flux. And here's where Gauss's law comes in. What Gauss discovered was that the total flux through a closed surface, and that's very important that we know we're talking about a closed surface, and those are things like cubes and spheres and cylinders with caps on the ends, but not things like circles and triangles, those that just have two dimensions. You clearly have to have an inside and an outside. And that's because this q that's in the numerator of this fraction over here means the charge that is enclosed within that surface. We refer to these surfaces as Gaussian surfaces. So every time you do something with Gauss's law, you always refer to, and I usually recommend you draw, what's known as a Gaussian surface. So you'll be drawing things like spheres and cubes and shapes like that. And then we have our permittivity constant, which we were introduced to when we first saw Coulomb's law. It is a property of space or a material that just says something about how electric field information is able to pass through it. And that's about as far as I'm going to go with that now. So it looks a little cryptic at first, and it's not until you use it several times that you start to get a feel for how that setup helps you. So let's take a look at some simple questions, and you might call them silly here at first, just to get used to using it. So I've drawn a three-dimensional situation here in just two dimensions. These three-dimensional surfaces are pretty tough to draw on a screen, so I've just got these cross-sections. I've got four surfaces here that I imagine are kind of wrapped around either three charges, or maybe two, or maybe one, or maybe none. And the question would be, how much net flux is through each of those surfaces? So if you could picture the field lines piercing through there, maybe going in, maybe going out, and imagine doing the calculation of the flux, which would be very cumbersome. Gauss's law allows you to say what you're going to get for your answer without doing the brute force multiplication and all of the calculus. So here's how we do it. If we take surface 1, surface 1 is the red one, that's here, and we say, okay, what are we going to get for the net flux through all that? Gauss's law says don't do the calculation here of the integral of E dot dA. Instead, look at the enclosed charge within that shape. So what do we have here? We have a minus 2q and a plus 1q. And those are the only two charges we're going to count because the other one, the minus q down below, is not inside or enclosed within that Gaussian shape. So the net charge enclosed there would just be a minus 1q. And then if we put that over epsilon sub naught, that is the net flux through that surface. Just as simple as that. Let's look at surface 2. Surface 2 encloses a plus q and a minus q. Well, what does that give you for a net? Well, those just cancel out and you get 0. So the net flux through surface 2 is 0. And that doesn't mean that you wouldn't see field lines piercing in or out. It means for as much flux as you have coming out of the surface, you're going to have just the same amount going in for a net flux of 0. That word net is very important there. And if we skip to surface 4, this is a trivial one because it's not enclosing any of those charges. And so there you also get 0. Now again, just because it doesn't have charges inside of it doesn't mean there aren't field lines piercing it. I mean, if we could draw, it'd be a mess, but if we could draw all of the field lines associated with those 3 charges, we'd have them going in and out of everywhere. And certainly they would be piercing all 4 of these surfaces. But the net flux is what we're finding through Gauss's law. And then surface 3 would be done in a similar way. Notice it is enclosing all 3 charges there, so that's minus 2, plus 1, and minus 1, and so that's a net of minus 2, and then that's over epsilon sub naught as well. So that's how we calculate the net flux through a surface using Gauss's law. Here's another kind of question very similar to this. It allows us to predict what is inside of a surface. So if we imagine a Gaussian cube now, and we somehow know the electric field strength at each of those 6 faces. Now this is completely ridiculous. There's no way you're going to have different electric field strengths and 6 different faces, especially have them be uniform across the face. But again, these are silly questions just for an exercise of getting used to it. So if we know this is a cube and all of those areas are identical, then we should be able to get a measure of whether we have a net positive or a net negative flux. So let's do this. A calculation of flux. Again, we're multiplying the field strength times the area. And because all of the areas are the same, I'm going to kind of ignore that part of it. So I just need to look at the field strength. And because flux can be positive or negative, that's going to be real important here. When you do Gauss's law with closed surfaces, any flux coming out of that surface is counted as a positive. So I'll mark some positives here, like the one back here at the back face, and the one here on the hard to see left face, and the one at the bottom face. Those are all positives. But the other 3, because they are coming into the surface or moving into the surface, we count that flux as negative. So that's a negative 15, here's a negative 15, and here's a negative 20. So if we look at all the positives and negatives, our positives add up to 40. It's a 15, a 15, and a 10. And the negatives, that's a 20, a 15, and a 15. That adds up to a minus 50. So the net flux is negative. And so what that tells us is that there could be a whole bunch of different charges in there. We don't know if there's pluses and minuses or all of one or all of another, but we know that there is a net negative charge somewhere inside that cube. We don't know where they are, we don't know exactly how many there are, only the net flux. So there's some questions just as an exercise. Now here's some practical questions that we might want to answer with Gauss's law. Imagine we have this odd-shaped, kind of a kidney-shaped hunk of metal. And we're going to charge it up with some positive or negative charge. And we put a wand on it that has some charge, or we touch it to something charged up that's different. Where will that charge go? Well, it turns out with Gauss's law, we can show that all of the charge ends up going to the surface of this. And so I'll draw a few. Let's say we charge this thing positively with a wand of some kind, or we plug it into a voltage source like we've done in the lab before. So I'm going to try to prove that none of the charges actually reside on the interior of the metal. And this is true whether the metal is a solid hunk of metal or whether there's little pockets of air inside there. Here's how we do this with Gauss's law. We first start with a premise that there cannot be any electric field inside of a piece of metal. And I, in class, demonstrated why that has to be. I'm not going to go through that again, just in the interest of time. But if there's no electric field anywhere inside the metal, then if I imagine this little Gaussian surface here that I've drawn dashed, that means that there's no field at that location where the dashed line is, because that's clearly on the interior of the metal. So if I do a flux calculation, again, I'm going to go around to every point on that little surface, and I'm going to multiply the strength of the field times the little size of the area. Well, you see I'm going to get 0 everywhere because E is going to be 0. That means my net flux is 0 for that surface. So now I go to the other side of Gauss's law that says that has to be equal to the enclosed charge divided by epsilon sub naught. Well, that means I must not have any enclosed charge. So the Q is 0 inside. I'm not talking about on the surface. I've clearly left myself inside. So that means none of our excess charge must be inside there. Just as simple as that. Almost feels like we did a trick there. And in some respects, Gauss's law is a bit of a trick. He was a brilliant mathematician who saw things just conceptually that most people could not. And he wrote it in such a simple way that allows us to use it for practical things like this. Here's another question. What if I took a metal ball, put it on the end of an insulating stick, and I brought it close to a point charge? How would it deform the electric field created by that point charge? Gauss's law can be used to prove that electric fields have to be perpendicular to pieces of metal when you're just outside of them. So there's no field inside, and immediately on the outside of each surface, the field lines have to come off directly perpendicular to the surface, which means that when I bring the ball near the field lines, it has to deform so that they, almost like they're trying to move in towards the center of that ball. And so we get a strange pattern like that. I like this picture I stole from the internet because you can see how the electrons on that metal ball polarize themselves and they move close to the point charge that's positive. And that's why we have a place for those field lines to kind of terminate. Each one of those negative charges is a place for a field line to terminate. And they're all originating on the point charge. So that's just kind of a little trivial thing there. Here's another question. How does placing a metal sphere around a point charge affect its field? So kind of similar. So here on the left, I've drawn what I hope is a very normal looking electric field. I may add to it here a little bit. Outward field lines, just a representative sample of them. 8 is a really common number for me to draw. Well, what happens if we take a sphere of metal? Not a charged sphere, just a hunk of metal. Maybe we start out as 2 hemispheres and we kind of take them up and we bring them together with the point charge inside. So now it's just one hollow shell of metal that has a point charge inside of it. What happens to that electric field? Well, again, we're starting with the premise that you can't have a field inside the metal itself. So you see how here on the left there's kind of a discontinuity in the field lines right there. They end right here and they start again there. Here's the other thing to notice. There's absolutely no effect out here. By putting that shell around it, we would never even know that the field is any different. The field lines look exactly the same as if the shell were not there at all. And that will be true as long as we didn't bring in a charged shell of metal, just a kind of an empty or neutral shell. So other than that little discontinuity where the metal itself is, we have no change whatsoever. And then we can extend this to even more interesting examples like, well, what if the shell itself brought some charge along? Then how would that field look differently? But I'm not going to go through every example here because we could be here all day. So I'm going to stop here, just trying to give you a little taste of what the power of Gauss's law can be. So as many different situations as you can try with Gauss's law, I think you'll just get more and more comfortable with using it. So we'll end here, and I'm sure you're going to get a little bit more with your homework problems and things I'll do in class or whatever class you might be in.